All right, so here we go. Find the probabilities. Probability of being male. So that's 68 out of 170. And what does that reduce to? 68 divided by 170 is 40%. Probability of being Republican. So that's 60 out of 170. So that's 35.353. So 35.3%. Republican, given that you're male. So that means we know we're only looking at the males. So that's this row. And who are the Republicans? Well, there's 24 male Republicans out of 68 total. So this is 24 out of 68, 24 out of 68, and that reduces to 35.3%. Notice it's the same as this. Probability of male given that you're Republican. So now I'm only looking at the Republicans. So that's 24 out of 60. And 24 out of 60 is 40%. Okay, so that one's done. Now, the interesting question, is gender independent of party preference in problem number 1, and how do you know? So the answer is yes, it's independent. How do we know? The definition of independence says the probability of A is the same as the probability of A given that something else has happened. If that's true, then A and B are independent events. So if we look up here and we say, well, the probability of male is equal to 40%, but the probability of male given that Republican has happened is also 40%. So in other words, if I tell you a person is a Republican, then they're 40% chance of being male. If I just say, well, what's the probability of somebody being male in the table overall? It's also 40%. So therefore, being a Republican has no bearing on whether or not somebody is a male. And if you do the female, it didn't ask us to, but notice the probability of being female is 102 out of 70, which is 102 out of 170, which is 60%. And the probability of being female given that you're a Republican is female given that you're a Republican is 36 out of 60, which is 60%. So if Republican happens, female happens at 60% rate, but female happens at 60% rate overall. Therefore, yes, the two events are independent. Required a little bit more space unless you just simply said these two events are equivalent, therefore they're independent. That's fine. Question 3, you're dealt a hand of 4 cards from a standard deck of playing cards. What is the probability that you're dealt all 4 aces? We've got a 4 out of 52 chance for the first ace, times a 3 out of 51 chance for the second, times 2 out of 50 chance for the third, times 1 out of 49 chance for the fourth. Multiply those together, and we get 24 out of, and that's 52 times 51 times 50 times 49 is 6,497,000, 6,497,400, which is 24 divided by that, an incredibly small number, 3.69 times 10 to the negative 6th, or 0.00000369. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, there we go. You roll 5 dice. Find the probability that none of the dice show a 1. Well, the probability of getting a 1, well, that's 1 out of 6. Well, I don't want any of the dice to have a 1. So the probability of not getting a 1, or we would actually write this as 1 complement, is equal to 5 out of 6. Well, I need that to happen 5 times in a row. So it's going to be 5/6 raised to the 5th power, because there's 5 of them in a row. So 5/6 times 5/6 times 5/6. So what do I have? I've got 5 out of 6, and it's raised to the 5th power. And I get 0.4018. And number 5, you roll 5 dice, find the probability of getting at least 2 6s. Okay, so the probability of getting a 6, right? So the probability of getting a 6, That's 1 out of 6. So I need at least 2 of them. Well, this is a binomial setting. I've got 5 trials, so I've got a fixed number of trials. I've got a fixed probability of getting a success. I have independent trials, and I'm interested in getting some number of successes out of a total possible set of outcomes. So it fits the binomial experiment. So I know that I'm going to do a binomial CDF, and I'm going to, well, before I continue, I'm going to think about this. I go, well, how many 6s can I get, right? I could get 0 6s, or 1, or 2, or 3, or 4, or 5, or 6. Oh no, just 5. All right, well, I need to find the probability of getting 0 6s. Well, actually, what I really want to find is the probability of getting from 2 through 5 amounts of 6s. And I want to add those probabilities together. But remember, the CDF command will not add those probabilities for us. It starts from the left and ends on the right, but it always starts at 0 and ends where you tell it. So I can't start it at 2. So I'm going to do binomial CDF. And I'm going to tell it that there were 5 trials. The probability of success was 1 out of 6. And I want to add up a 0 and a 1, add up the first 2 of these. And so that gives me an 80% chance. So the probability of getting these guys is 0.804. So the probability of getting these guys is the rest. So 1 minus 0.804. So 1 minus that is 19.6%. So the answer to this question is 0.196.